All right, thermodynamics. We've covered this a little bit in Gen Chem 1. There are three main terms, well, and we'll go with four-ish, but three main terms in thermodynamics: delta H, delta S, and delta G. Delta H, enthalpy. We discussed that in Gen Chem 1. Delta S, entropy. We might have discussed it a little bit in Gen Chem 1. We're going to really start doing stuff with it now. Delta G, Gibbs free energy. We'll discuss that in this chapter also. The fourth term that goes along with thermodynamics is K, the equilibrium constant. The equilibrium constant is a thermodynamic term towards the end of this chapter. We will show how K, our equilibrium constant, is related to delta G and delta H and delta S. But let's go through thermodynamics. And we'll start with the second law of thermodynamics. It just states that energy tends to dissipate. It tends to spread out when not prevented from doing so. Energy does not like to be bottled up. It needs to be spread out over as many different places, as many different states as possible. All right, that's just what energy likes to do. All right, so our first definition here is a spontaneous process, a process that occurs without ongoing outside intervention. An example from physics would be if you had this block of wood or something like here and you had a ball on the top. If you set the ball on the top and then let it go, it will spontaneously roll down that block of wood. It does it spontaneously. No matter how many times you put that ball up there, if there's nothing blocking it, it rolls down this because it's going from higher potential energy to lower potential energy. So this is spontaneous. No matter how many times you set the ball at the bottom of the ramp without any outside forces, the ball is never going to spontaneously go up the ramp because spontaneous reactions, spontaneous processes go from higher potential energy to lower potential energy. And that in general is the same as chemical reactions. If there's no outside influence, reactions want to go from higher energy, higher potential energy towards lower potential energy. All right, something to note, this doesn't say anything about the speed of the reaction. Recall from previous when we had potential energy versus reaction progress diagrams, say in Gen Chem 1, we have in kinetics, in our Gen Chem 2 kinetics, where we had reactants going to products and we have this hill here. Recall this was our activation energy. In our activation energy, the height of this hill told us how fast the reaction is going to occur. This activation energy is the kinetics. The higher the hill, the slower the reaction, because the fewer collisions will have the proper energy to result in products. So this energy term here, this potential energy term where we're looking at the energy difference between the reactants and the top of this hill is our activation energy. That's kinetics, that's speed of reaction. When we look at the energy difference between products and reactants, this is our thermodynamics. This is related to equilibrium constants, to endothermic or exothermic. Note from our kinetics chapter that because this is higher, the products are higher in energy than the reactants, we had to add energy. We didn't get all that energy back. We had a net input of energy. This is an endothermic reaction. And so this term here, the difference between reactions and products in terms of energy, is our thermodynamics. In general, this reaction here, as written, would not be spontaneous because we go from lower energy to higher potential energy, whereas a spontaneous reaction usually, most often, is from higher potential energy to lower potential energy. So in general, this would not be a spontaneous reaction. In general, endothermic reactions are not spontaneous. So, however, you can get a non-spontaneous process to occur if the proper conditions are provided. All right, we can make things go from low energy to high energy and stay at high energy as long as we have the proper conditions that supply that energy. All right. But people noticed something. They were looking at these curves here and found out there are some reactions that are spontaneous. They go, but they are endothermic. Now, they're not hugely endothermic. They're a little bit endothermic. They get colder. They take in heat from the outside. How can this happen? How can a reaction occur if the products are at higher potential energy? And that's just not the way spontaneous reactions tend to go. They realize there must be another term in there, another issue to look at, and that issue is entropy. Right? Some processes are spontaneous, but endothermic. And for example, if you're above 0 degrees Celsius, ice will melt. It takes in that heat. The water is a higher temperature than the ice, but that's a spontaneous process. If you take solid sodium chloride and put it into water, it will dissolve into Na plus and Cl minus. And it gets a little colder when it does that. That's an endothermic process, but it happens spontaneously. Why are they going to go if they don't go to higher potential energy? And the answer is disorder. Recall the second law of thermodynamics. Energy likes to dissipate. It wants to spread out. The more disordered your system is, the less order it has, the more spread out that energy is. And our term for this spreading out for our disorder is entropy. It's got the symbol S, and it's a thermodynamic function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. Well, what does that mean? Yeah, let's look into this. And truthfully, this whole next page and a half is just some derivations and stuff to let you know where it comes from. I'm not going to hold you to any of these calculations on an exam. It's just an idea to know where some of this entropy comes from. The main point in all of this is the more random a sample is, the more spread out it is. That means the more spread out the energy is. That leads to the way nature likes things. Energy wants to spread out. So reactions tend to go if they can go towards more randomness, towards more spread out energy. All right, so let's look at microstates and macrostates here. Ludwig Boltzmann here, 1800s to 1906, came up with this equation, as your book says. It's printed on his gravestone. The entropy equals the Boltzmann constant times the natural log of W, whereas W is the number of microstates. I'm not even going to make you worry about the Boltzmann constant. We're not going to do any of these calculations. But the number of microstates is simply the number of energetically equivalent ways to arrange the components of a system in a macrostate. All right, so one example is this. Say you have an ideal gas. It's at certain pressure, volume, and temperature. This is the macrostate. The pressure, as long as you don't do anything with gas, the pressure, the volume, the temperature will remain constant. That is the state of this gas. It exists a certain number of moles at this pressure, this volume, and this temperature. All right, but the question is where are all the individual molecules at any given instant? The position of all the molecules is the microstate. Now, if you had 1 mole of gas, 6.022 times 10 to the 23rd molecules, and you had to know where each of them are at a given instant, and then an instant later, where did they move to? That's a whole bunch of different microstates. So let's start very small when we're looking at it. Here's an example. Say we had a black dot and a red dot, and we only had one energy level, which means the black dot and the red dot had to be at that same energy level. This system has 1 microstate. But note, what if we had a black dot and a red dot, but we had 2 energy levels? Well, now we have 2 microstates. We could have the black dot in the lower energy, the red dot in the higher, or the red dot in the lower and the black dot in the higher. 2 microstates. Either way, we still have the same macrostate, 1 dot in each energy level. So the microstates are energetically equivalent, 1 dot at each energy level, but the microstates are energetically equivalent, and so the macrostate is the same, 1 dot at each level, but there are 2 different microstates. So this is a more spread out system than this. This is a more random system than this because it has 2 microstates, where this has 1. All right, let's look at this situation. What if we had a container that had a barrier here and we had, say, 4 molecules of gas on this side? Well, there's only one way you can arrange that. All 4 molecules on this side. This macrostate has only 1 microstate. But if we numbered our gas molecules 1, 2, 3, and 4, they gave them each a number and tracked them. How many different ways can we arrange this situation where we have 2 molecules of gas on this side and 2 molecules of gas on this side? Well, we could have gas molecule number 1 and number 2 on the left, 3 and 4 on the right. So there's 1 microstate of this macrostate 2 and 2. Well, here's another microstate, 1 and 3, 2 and 4, 1 and 4, 2 and 3. When we do all the permutations, we find there are 6 ways to arrange 4 different molecules with 2 on one side of the barrier and 2 on the other, which means this macrostate has 6 microstates. 6 microstates means the energy can spread out better. This has a higher entropy. This is a more random possible situation than this. So higher entropy, more spread out. This is more random. All right. And what that means is we don't often look at the entropy of a single system. We look at the energy of a process. So the second law of thermodynamics, for any spontaneous reaction, the entropy of the universe increases. Means if a reaction happens, the change in entropy of the universe is greater than 0, and the change in entropy is just the final minus initial. What it means then, the second law of thermodynamics says for any spontaneous process, the universe gets a little bit more random. Okay. So let's look at this. What if we started with this state? Let's have all 4 gas molecules on this side of our container. What would happen if we then opened up a little door in between these 2? What will happen? Well, some of the gas molecules will go over to here. Note, there was only 1 microstate when all 4 were on this side. Note there would be only 1 microstate if all 4 were on the other side too. So here's 1 macrostate. Let's say that again. This is 1 macrostate with all 4 balls on the left side, and that's also has 1 microstate. A different macrostate would have all 4 balls on the right side, but that would also only have 1 microstate. A different macrostate would have 2 balls on this side and 2 balls on this side. And we will see that in this, as we saw before, in this macrostate, there are 6 possible microstates, which means in this macrostate, the energy is spread out over 6 possible variations, which means this has higher entropy, which means that if we opened this door, we would eventually find we would have 2 balls on one side, 2 balls on the other side, because that's more random, has more microstates. And note, we would not expect, if we open this door, to just have all 4 balls on the right side, because that would, again, have a lower number of microstates, which means that macrostate would be less, let's say less disordered, would be more ordered, and that would violate the second law of thermodynamics if we're not adding any energy or anything like that. So that's a really, really long, complicated way of saying if you've got a bunch of gas molecules on one side and none on the other, if you open a door, it'll even out. But that's the deal with entropy. It evens out because there are more microstates when that evens out. And it's the same thing. If you're in a room and there's a skunk on one end of the room, if that skunk sprays one of your classmates at one end of the room, those molecules are not going to stay in that corner where where the skunk is. That skunk smell is going to go dissipate throughout the entire room because of entropy, because it's more random if it's spread out over the entire room. There would be many more microstates if the gas skunk smell molecules are all over the room. Okay, so let's look now at entropy and state changes. Change in state means going from solid to liquid and gas. Note, a solid is a very ordered system. We have all the molecules all nicely packed. A liquid is less ordered. Not a whole lot less ordered, but a little less ordered. The molecules are all touching each other, but they're a bit more random in their touching of each other. You don't have the nice order that you have in the solid. In a gas, it's a much, much less ordered system. Those molecules are just randomly going in random directions, independent of each other. So a gas has a lot of entropy, a lot of randomness. Solid does not have much entropy at all. Liquid has a little bit more entropy than a solid, but gas a whole lot more. So liquid a little more entropy than a solid, gas a whole lot more entropy than a liquid. And here's a nice equation. Our change in entropy of a solution equals Q rev. Q rev is the heat exchanged with the surroundings in a reversible process divided by the temperature. Recall when we learned delta H way back in Gen Chem 1, when you had the system and the surroundings, we're going to back to those terms. All right. Oh, here we are. The change in entropy of the universe, which, as you recall from the second law of thermodynamics, change in entropy of the universe always increases. The universe gets more random for a spontaneous process. The change in entropy of the universe is going to equal the change in entropy of the system plus the change in entropy of the surroundings. You got the system and the surroundings because that's where energy can flow. All right. So let's look at this. Note, when water freezes, it becomes more ordered, which means water is freezing to form ice. The entropy of the system goes down. It becomes more ordered. Well, how is it possible for the system to get more ordered? The only way it's possible is if the surroundings become less ordered. Because if you put ice, if you put water at -1 degree Celsius, it will spontaneously freeze into ice. Water will spontaneously freeze into ice at normal pressure, at 1 atmosphere pressure, at -1 degree Celsius. That is a spontaneous process. The system does get ordered spontaneously, which means the surrounding must get disordered. And the surroundings must get disordered more than the system gets ordered, because the delta S of the universe has to become larger. The universe will become less ordered even if a system becomes more ordered, because the surroundings become even less ordered than the system became ordered. And what do we mean by the surroundings? The surroundings is literally everything else in the universe. The universe is your little reaction and everything else in the universe. Your system is your little reaction, your solution, or your reagents, and everything else in the universe is the surroundings. Okay, so yeah, while the entropy of the system might decrease, entropy of the surroundings will increase more. All right. So an exothermic process increases the entropy of the surroundings. An exothermic process gives off heat. Turns out heat increases the entropy of the surroundings, makes the surroundings more random. An endothermic process decreases the entropy of the surroundings. Note delta S equals Q reversible, we won't worry about that, divided by T. And so if we're looking at the surroundings, we said, which is the rest of the universe, we know the surroundings, the rest of the universe, is pretty much infinitely large. If you're looking at the reagents in a beaker, the rest of the universe is huge compared to the reagents in the beaker. Yes, there's little fluctuations on Earth, but the universe pretty much has a constant temperature. Outer space has a definite temperature that is constant. and constant pressure. There are little pockets of higher pressure called planets and gas clouds and stuff like that, but in general, the universe is fairly infinitely large at a constant temperature and a constant pressure. And under these conditions, Q, the heat exchanged, equals delta H under constant pressure conditions. Also, we learned that the heat taken in by the system equals the heat given up by the surroundings and vice versa. Q of the system equals negative Q of surroundings. Therefore, we can take this equation here and realize since Q delta S of the surroundings is negative delta H of the system divided by temperature. All right. I'm not going to make you responsible for knowing or for deriving this or even worrying too much about these types of equations. Some people might get jazzed by this. I do not. But we needed to note that our entropy value is related to delta H. The change in entropy, the change in randomness of the surroundings is equal to the heat gained and lost, the enthalpy of our system. All right, and we will look at that when we start our next video dealing with Gibbs free energy.